Hello everyone. Today I will give a talk on my work solving multi-trip time-dependent multi-vehicle routing problem. I will present the dynamic programming-based algorithm we proposed to solve this problem in this video. Here we show the outline. First, I will introduce the problem we are facing, and then the heuristic method we are using. Subsequently, for each potential solution found by heuristic method, we use dynamic programming-based algorithm to split the gen tour into several trips for several vehicles. And lastly, I will show the partial results tested on the real-world data from Singapore Coca-Cola Company, followed by the conclusion in the end. So the vehicle routing problem is a very famous combinatorial optimization problem, which asks that what is the optimal set of routes for a fleet of vehicles to traverse in order to deliver all the given customers. So each time we use a vehicle, we need to pay for a fixed cost. And multi-trip is a very common and realistic variant of vehicle routing problem, where each vehicle can perform several trips within a workday. And time dependent is another realistic variant, where the speed of vehicle is no longer constant, but a step function generated based on the city's rush hour timetable. So our problem considered these two conditions to find a route to serve all the customers, where each customer has a corresponding service time and demand. The vehicle with capacity Q must depart from depot and back to the depot and in the end. So the objective function of our problem is to minimize the sum of total travel time of all the trips and the fixed cost of used vehicles. The figure shows an example of 14 customers served by 2 vehicles with 5 trips in total. So the solution represented by a gen tour, which is a sequence of customers served by vehicle 1 trip 1 and vehicle 1 trip 2, vehicle 2 trip 1, and so on and so forth. We connect them together and get the gen tour, discard the depot of all the trips. So after the time-dependent split algorithm, we need to find out how to assign them to different vehicles. And for each vehicle, how to split them into several trips. And also at the same time, determine the departure time of each trip. So the research gap of this work is that this is the first time to model and solve time-dependent multi-trip vehicle routing problem. And also the first time to extend the split algorithm to time-dependent condition and also use the dynamic programming-based algorithm. And the third one is that for the multi-trip algorithm, for the multi-trip vehicle routing problem, the most common approach are the use the heuristic method with the bin packing algorithm, and our algorithm is only use the heuristic with a dynamic-based programming. And so the heuristic part, we use the mimetic algorithm, which is the hybrid genetic algorithm with some local search operators. So with this, we can generate sufficient and efficient gen tours. It combines the advantages of both population-based approach, which can explore a very wide range of search space, and with the local search operators can make the search intensively. So now we introduce the time-dependent citing. So the different with the classic vehicle routing problem where the speed of vehicle is always set to 1, and we only need to find out the route with the minimum travel distance. The time-dependent vehicle routing problem assumes that the speed profile of each edge ij is a step function. So it considers the peak hours of a day. And the speed of vehicle is split into several time zones, and it will change only at the end of each time zone. So in the first picture, we can see that the travel speed function is a step function, and the resulting travel time function of departure time from node I is a piecewise linear function, which can be calculated and represented by two groups of breakpoints. So the Wij 0, 2, 4, and 6 and 8 are the speed breakpoints, and the travel time breakpoints are the Wij 1, 3, 5, and 7. For example, when we departure from node I after time Wij 1, the vehicle will experience a change of speed when it travels from node I to node J. So we can get the breakpoints for a simple edge, but we want to get the breakpoints for a route, because we know that the sum of piecewise linear functions are still piecewise linear function. So when we want to find out when the objective function is something about travel time of a route, then we can just find out to calculate all the solutions of the breakpoints, because the best solution must be one of them, right? So how to calculate the breakpoints of a route? First, we can use a back-forward process from the last two nodes updated until the first node's depot. So as this figure shows, the backward propagation process from Ti to Ti plus 1. First, the breakpoints of Ti plus 1, there are 3 original breakpoints, and we calculate the corresponding departure time of Ti, and then we update the node Ti's breakpoint site. Then we have two parts. The green ones are the original ones, and the blue one are updated from node Ti plus 1. And then using this updated breakpoint site to update node Ti minus 1's breakpoint site, then we can get 6 new breakpoints, the blue ones, and the yellow ones are the original ones. So in total, we can get 11 breakpoints for Ti minus 1, and so on and so forth. The same process will repeat it until we go back to the depot, the first node. Then we can get all the breakpoints of a whole route. We use this to find out the optimal solution for a Gen tour. So we use the dynamic programming-based algorithm, which is used to find the allocations of vehicles and their trips, and also determine the departure time of each trip. So we set the state as 3 dimensions. The first one is Ti, and the second one is the breakpoint of Ti, the J's breakpoint. It means time. And the third one is the so far we use how many vehicles we use is HV. So DP value is the minimized cost of this software, from 0 to Ti. the minimized cost. So with use HV vehicles, and the departure time of TI to depot is J spring point. So how to update the time for DP, TI, BP, IJ, HV? We have 5 different transition situations in total, and we show for TI to how to update DP value of TI's J spring point, and when we use HV vehicles in total. The first transition is that when TI is the first node of a trip, but and it is the only node served by this trip. So it means we departure from depot and visit the TI and then go back to the depot. The total travel cost from depot to TI is this. We updated from TI minus 1's departure time BP I minus 1K. So it must satisfy that the case spring point of TI minus 1 is early enough to ensure that it can go back to depot and departure again and reach to no TI in time. So this is the first transition, and the second one is similar to this one. The difference is that we use a new vehicle for TI. So we need to pay for a fixed cost for a new vehicle, but we don't need to consider the departure time of last trip, which means the TI minus 1's trip. It can departure from this node at any time, and we use the minimize solution to update the TI's state. Okay, so the third transition is that when the vehicle waiting at the depot, it is like we need to avoid peak hours, so we just wait at the depot. And the first one is that the TI is the last node of current trip, but this trip is not from a new vehicle. It means for example, this purple edge, and this trip, so 2 nodes, T3 and T4, and so the departure time of T1 must as early that we can departure from the depot and then get to the T3 at its J spring point. So they need to satisfy some relationship of the departure from last trip and this trip. And the fifth transition situation is very similar to the fourth one, because the difference is we change a new vehicle, so that we no need to consider the departure time of last trip and this trip. But also, this trip need to satisfy the capacity of the vehicle, and the maximum travel distance cannot bigger than the constraint. And this is all the transitions of the dynamic programming. So then we can test on the database. So because this is a new problem, the time-dependent multi-trip problem, so we give the benchmark. We generate new data on real-world data from the Singapore Coca-Cola company. They provide the the real world data, and we show it in the real world trip map. So we try different initial clustering method for the mimetic heuristic method. We including the KNN and K-means, this kind of clustering method, and we can see that the optics can have the best performance in average, and so because the real world data, the customers must have some relationship clustering in potential, because in real world data there are some residence hall and something else, so the random always perform not as good as others. Then we subsampling the data into small scales where only have 10 nodes. We compare the time and the best solution with the MIP solver, and finds out that our algorithm can always find the best solution for all cases, but we use much shorter time. And we also found out that when we set different fixed cost of a vehicle, the number of vehicles are different. And when we set different capacity of a vehicle, we can get different trips. So it is important to set different penalties and the capacities constraint for the problem. So we provide the benchmark for this time-dependent multi-trip vehicle routing problem. And this is the first time to solve this problem. Hopefully others can compare to solve this problem with some other methods and compare with this benchmark. Finally, we compare with a classic CVRP problem. So we can find out that we can get optimal solution, the best solution with small scale data. So in conclusion, we consider two realistic variants of vehicle routing problem, which are the multi-trip vehicle routing problem and time-dependent vehicle routing problem. So we first propose a multi-trip split algorithm to solve the multi-trip multi-vehicle routing problem based on the heuristic algorithm. And then we model and solve a new problem, the multi-trip time-dependent multi-vehicle routing problem. And we propose a formal description and a mixed integer programming model for this problem. And we generate new benchmark test instance on real-world data from the Singapore Coca-Cola company, and compare the performance with the off-the-shelf solver, the Groovy, and we can find that we solve the optimal solution with much shorter time. And finally, we develop a dynamic programming-based algorithm, the TD split, to find out the allocation of each vehicles. And for each vehicle, we split the tours into several trips for them. And then we provide the benchmarks for multi-trip time-dependent multi-vehicle routing problem. So this is the first time to extend the split algorithm to time-dependent condition, and also the first time solving this both the multi-trip and multi-vehicle and time-dependent variant of the vehicle routing problem. So that's all. Thank you for listening.